right. Give people a minute to join, I guess. I assume you all turned in homework 3. Maybe there's some stragglers who are just doing it, joining late. There was a lot of discussion on Piazza about homework 3, so either it was somewhat difficult homework, or you guys are getting more serious about the course. It's one of the two. I hope it's the latter. You're more interested in the material. All right. So I need a mic check. So you guys can hear me, because last time we had some problems.
Yes.
Okay.
Yeah, I can hear.
Alrighty. Okay, so let's, as usual, briefly review what we were talking about last time, which was Lagrange multipliers with the equality constraints, right? And the main result is that was the necessary conditions for optimality, which was if x star is a local minimum, then there exists a unique lambda such that this gradient condition holds. So it's not just that the gradient of f at x star is 0, but it's actually when you add the sum of the linear combination of the gradients of the constraints, that becomes 0 at a local minimum of the constraint optimization problem. And these lambda i's are called the Lagrange multipliers. Okay, and then we went on, and this was actually based on lecture 11. This is what we proved in lecture 11. And then we went on to see what the second order necessary conditions would be, assuming twice differentiability again. And then what we concluded was that, well, actually, maybe we should just go to the result, which is on the next page, in terms of the Lagrangian. So the second order necessary condition says that this Hessian of my Lagrangian function with respect to x, okay, satisfies this condition that it's when you pre-multiply by z transpose and post-multiply by z, you get something non-negative for all. It doesn't, not for all z, but all z such that hi transpose z equals 0. So all z belonging to this v of x star set, right? A space, right? The space of first order variation, feasible first order variations, as we discussed in lecture 11. Okay, and then we said, well, actually, you can go on to show sufficient conditions, second order sufficient conditions as for a local minimum. And the second order sufficient conditions are similar in that if suppose x star is feasible and regular, this has to be satisfied. If there exists a lambda such that this is 0, the gradient of the Lagrangian is 0 at x star, and if the condition on the Hessian is actually satisfied with a strict inequality for all z not equal to 0 and z belonging to this v of x star, then x star is a local minimum for the constraint optimization problem. So usually what we do is use the first order necessary conditions to find possible candidates for a local minimum, right? And then we use the second order sufficient condition to check whether those are actually indeed local minima or not, okay, to verify. Okay, if you a lot of these problems, you only have one candidate to check, and so you just have to check that candidate, check this condition for that candidate, okay, to verify whether it's the local minimum or not. Okay, and then we did some did an example. One thing I want to re-emphasize here is that a lot of times when you want to when you establish something as a local minimum, you also may want to know whether it's a global minimum or not. And so you can use various ways to show that. Convexity, of course, is an obvious way. So if the function is convex and the set on which you're defining things is convex, then then you know that every local minimum is going to be a global minimum. So that's not a problem. But sometimes maybe you don't have convexity, but you may have something like coercivity. So if the function is coercive, then on a set that's closed, that's not necessarily compact, then it achieves its minimum on S. And this, again, intuitively, think of a picture where you have a coercive function that blows up as x goes to infinity, okay? And then if the set S is such, if it's not compact, if it's not bounded, essentially, if it's closed, but it's not compact, so it's not bounded, then anywhere on that set, the x goes to infinity, this function is also going to go to infinity, okay? And so since it's blowing up, it must have a minimum. Okay, so and then the proof is very similar to the corollary of Weierstrass's theorem that we proved earlier. So you might be able to use this result in some cases to establish that something is a global minimum. Okay. All right. So I think now there was also one other result about sensitivity analysis. And to show that if the constraints perturbed by a little bit, then the optimization problem, the solution, the value of the optimization problem changes, and the amount by which the rate at which it changes with respect to the perturbation is actually can be interpreted as is the Lagrange multiplier. So that's one interpretation of the Lagrange multiplier. That's actually useful in some applications. Maybe we'll get to talk about that towards the end of the course, okay, when we focus more on applications. Okay, and so let's go get on with today's lecture. All right, so we're going to be, today's lecture is just going to be examples, okay? I'm going to focus on linear constraints because they have some special properties. So examples with linear constraints, okay? And then on Thursday, we're going to do a review for the exam. So if you have any questions about the exam, bring them. And actually, it'll be a review of the entire material. So anything that we have done until lecture 12, I guess, which is relevant for the exam. Actually, today's lecture is also relevant in a way for the exam because I'm just doing examples. So you can bring any. I'm not going to teach any new material on Thursday. So if you guys don't come with questions on Thursday, then we're just going to end early. So you better come with your questions, okay? And then maybe we'll go over some. So someone asked on Piazza whether there would be a practice exam. So I've never taught this course before, and so I don't have any of my old exams that I can put up. But I'm going to try and I also teach it a little bit differently than other people have taught it. So it would be hard for me to give you a sample exam that's close to what your actual exam will be. But there is one version of the course that was taught by Professor Srikanth a few years ago, which comes close. And so I'm going to put up his exams on the website for you to look at with solutions. Okay, I got his permission to do that. So I'll put up that on the website, and then maybe we'll go over some of those questions and any other questions you may have. Okay, so that'll be Thursday. I'll send an email about that as well. Okay, so any questions about what we talked about last time?
I have a logistic question. So
Yeah.
is the cheat sheet or notes allowed in exam? If so, like how many?
Oh yeah, so I actually thought about that for a while, and I think so. The CBTF has some options, and they do have the option of allowing you to have have a cheat sheet. Actually, they say only one, but for this exam, I'll only allow one cheat sheet. So one 8.5 by 11 letter paper size thing. It's on the website. It's the details about that. So one sheet, both sides, and if you don't have clean handwriting, if you want to type something up and print it, that's fine with me. But it's just one sheet of notes that you'll use. I think it'll be much better for you to do this than to rely on open book, open notes, because this will allow you to collect your thoughts together and make sure that you have all the key results that for the material that I've taught so far at your fingertips. So you'll be able to answer the questions more efficiently. So, and plus also the reason why I didn't want to put down open book, open notes is because not all of you are going to have the textbook, and I can't give you access to, I'm not going to give you access to random websites on the internet. So that option will be turned off. So all you'll be able to see on your screen, computer screen, will be your exam, nothing else. And so to be fair to everybody who may or may not have printers or whatever at home, so I thought everybody can at least handwrite one sheet of formulas that they can use for the exam. So I'm sticking with that. So I'm not going to change that. Okay. Any other questions? All right. Okay. So let's talk about equality constraints where the equality constraints are linear. Okay. So basically, I want to minimize a function f such that some a matrix A times x is equal to b. Okay. So, and this matrix A, I'm going to think of it as having m rows. So the m constraints and all. So m rows. So, and the rows are going to be denoted by A1 transpose A2 transpose AM transpose, and B has m elements like this. Okay. So if you look at the constraints are the m constraints hi of x are constraint functions rather are ai transpose x minus bi. Okay, I equal to 1 to m. All right, and so because hi of x equal to 0 means that ai transpose x equal to bi. So that's the ith constraint. Now, if you take a look at the gradient of this, it's very easy to compute. It's just ai, right? The gradient of hi is ai. Now, if the ai's are linearly independent, for which how should m and n be related? So x is n-dimensional. So how should m and n be related for the ai's to be linearly independent? So if I have m n-dimensional vectors ai, when are they? What condition on m should be satisfied for them to be even possibly linearly independent?
Less than or equal to n.
Yeah, so m has to be less than or equal to n, right? And we already know this from our, existence of Lagrange multipliers. So let's say m is less than or equal to n, and if the ai's are linearly independent, then all x belonging to Rn are regular, right? Because this gradient is not really a function of x. It's just AI. So the AI is linear independent, the gradients are going to be linear independent for all x. So all x are regular in this case. So if x star is a local min, and the corresponding Lagrange multiplier, we know that unique Lagrange multiplier exists, and it satisfies this equation, right? That the gradient of f at x star plus the linear combination of the gradients of h is equal to 0. So we can rewrite this in terms of AIs as saying that the summation, I'll take the summation I equal to 1 to m lambda I, and the gradient of this is AI. So this must equal minus the gradient of x star. Okay, but I can actually rewrite the left-hand side of this equation in terms of product of a matrix and a vector. And anyone want to tell me what that matrix and vector are? So what do I put on the left-hand side? The right-hand side I'm going to leave unchanged, but the left-hand side I'm going to write as a product of a matrix and a vector. What's that matrix? What's that vector?
A lambda.
Let's see if it's A lambda makes sense. So on the right-hand side, I have an n-dimensional vector, right? So A lambda would be an A times lambda. In fact, it's not even, you can't even multiply it because A is an m by n matrix and lambda is an m dimensional, little m dimensional matrix. So if m is less than n, you wouldn't be able to even multiply those two. So what should it be?
A transpose lambda?
A transpose lambda, that's right. Because basically A transpose will look like, we'll have columns that are A1, A2 up to AM, and this is an n, A transpose is an n by m vector. And now if I multiply this by a matrix of the lambdas, sorry, not matrix of lambdas, vector of lambdas, lambda 1 through lambda m, if you multiply that by that, then basically the first column gets multiplied by lambda 1, second column gets multiplied by lambda 2, and so on. So you do get the lambda AIs and summed up, right? So that's why this is A transpose times lambda. And the dimensions also work out then. Because this is an n by m, this is an m by 1, this is an n by 1, okay? Okay, so what about, so this is a set of n equations, right? And then we also know that x star satisfies the constraint. So what is that? A x star must equal b. So this, and this gives me m equations. Okay. But suppose, let's look at the case where m equal to n. Okay. Then A is an n by n matrix, which is actually full rank because we are assuming that the columns of A are, or the rows of A are linearly independent. So this is also full rank. And so x star then becomes unique. So I can actually solve this directly, the constraint equation directly. I don't even care about the Lagrange multipliers because the x star is unique. And I don't have anything to do anymore if x star is unique. So x star is just A inverse B. And we know that if there's only one value of x that meets the constraint, right? There's only one value of x that meets the constraint. That is the solution to P. It's the only value, right? So it's the maximum, it's the minimum, whatever you want to call it. It's just one value. Okay, so it's not that interesting if m equal to n. Okay, so then let's look at the case when m is less than n, strictly less than n. Okay, so in this case, A is an m by n matrix with rank m. Then actually, since it's we have now fewer equations than unknowns in Ax star equal to b, then we have infinitely many solutions. to this. Okay, so because we have fewer constraints than unknowns for in X star. But then we also need to satisfy the Lagrange multiplier constraints. So now the Lagrange multiplier constraints will turn out to be important. So we really need to solve for X star and lambda together using the equations A transpose lambda equal to negative, okay, and A X star is equal to B. So as I said, these are M plus N equations in M plus N unknowns. Okay. Now, of course, if the gradient of F at X star is linear in X star, then you have M plus N linear equations in X star and lambda, okay, and then the solution can be unique, right? For X star, again, and there'll be a corresponding lambda to the X star. But in general, this gradient of F need not be linear. For example, if F is not quadratic, it's not going to be linear, and X star, and so we may have multiple solutions. For the X star and then the corresponding lambda. Okay, so in that case, you may have to look at all the possible candidates for X star, candidate solutions for X star, and then check to see if second order sufficiency condition is satisfied. So second order sufficiency condition can be written, again, it's easy in this case because the Lagrangian is can be written in terms of AI transpose X minus BI, sorry. And when you take the gradient, you just get gradient of fx plus a summation I equal to 1 to m lambda I like we saw before. And if you take the Hessian, this is not a function of x anymore. So and so the Hessian is just going to be the Hessian of f. But you don't need the Hessian of f to be positive definite. All you need is need to check that if you take some z transpose the Hessian of f at x star times z, this should be positive for all z not equal to 0, such that the gradient of hi transpose z must equal 0 for all I. That's the same as saying ai transpose z is equal to 0. Okay. All right, so let's do an example to illustrate some of these ideas. So in this example, we're trying to minimize this function. We're trying to minimize this this function given here. This is my f of x, such that we have these linear constraints. So we can write these linear constraints as ax equal to b. So this can be written as ax equal to b, with a equal. So there are 3 guys. So it's a 2 by 2 rows, 3 columns, right? 3 values of x, 1, 1, 0, and 0, 1, 1. And then b equals 2, 1. Okay, so I can write these linear constraints as ax equal to b with this matrix A and this vector b, right? Okay, so now let's look at some of these things. So let's compute the gradient of f of x first. And this is easy to do. This is negative. The first component, take the gradient with respect to x1, you get x2 plus x3. And then the second one with respect to x2, you get x1 plus x3. And then you get x1 plus x2. Easy. And the gradient of h is the columns, the rows of the A matrix. So you get 1, 1, 0. And then, or you can actually take the gradient in this case, and 0, 1, 1. Okay. Easy enough to do. And we know that x star and lambda should satisfy the equations hi, the constraints equation hi of x star equals 0, I equal to 1, 2, and the gradient of f at x star plus summation to 0. So these are the equations, and that'll give me 5 equations and 5 unknowns. Okay, and those equations, I'm going to write them down. So the first one is based on the constraints. The first two, let's write them based on the constraints. x1 star plus x2 star equal to 2. And then x2 star plus x3 star is equal to 1. Put that there. And then the next one is from the lambda constraint. So the first one will give me the first component will be x1 of the gradient is x2 plus x3. So then that gives me just lambda 1 from that guy. So if we look at here, that's just not, this lambda 2 will have a 0 with it. So I just get lambda 1. So lambda 1 should equal or lambda 1 minus this x2 plus x3 should equal 0. Okay, and similarly lambda 1 is the plus lambda 2 for the second component, because I have this, and that would be minus x1 star plus x3 star. I should put it back. I should really be putting parentheses around this. Minus x1 star plus x3 star equals 0. And then the last one will be lambda 2 minus x1 star plus x2 star equals 0. Okay, so those are the 5 equations. And you can immediately solve some of this stuff because you see that x2 star plus x3 star is 1. So this will give me that lambda is 1 is equal to 1. And then lambda 2, similarly, lambda 2 is equal to x1 star plus x2 star, which is equal to 2. So this is equal to 2. Okay, and then this middle equation here, this middle equation says that x1 star plus x3 star is lambda 1 plus lambda 2, which I've just computed. So this is equal to 3. Okay, so now we can put these equations together. There are various ways to solve this. I'm just giving you one way. Okay, but there's linear equations solved in a variety of different ways. So if you take these last 3 equations and just add them up, you get 2 times x1 plus x2 plus x3 star equal the sum, 2 times the sum of the lambdas. Okay, so that's equal to 6. And that means that the sum of the x1 star, x2 star, x3 star is 3. And now we're done basically because we know that x1 star plus x2 star equal to 2. So x3 star must equal 1. Similarly, x1 star plus x2 star plus x3 star is 1, so x1 star must equal 2, and x2 star has to be 0 in that case, because they have to sum up to 3. Okay, so this is a unique solution for x star, and the corresponding lambda is just this 1, 2. Okay, so to check whether this is a minimum or not, we can kind of guess that it might be, but let's check to make sure that it's a minimum. So we need to check the second order sufficiency condition for this x star, which is 2, 0, 1. Any questions so far? Okay. So as we saw before, this is equal to 0, the Hessian of HI. So all we have to check is the Hessian of F. But the Hessian of F is actually very easy to compute from the gradient. So the gradient is here. So the first component is only a function of x2 and x3. So the Hessian 1, 1 component of the Hessian will be 0, and the other two will be -1, -1. Right? So so you get 0, -1, -1, and then similarly the second. This is just by symmetry. You will see that this is the case. Now, is this a positive semi-definite matrix, or even positive definite matrix actually? So if it's a positive definite matrix, then we don't have to worry about the V of x star condition. We are done, because then the condition holds for all multipliers. It's z transpose z, so we don't have to worry about checking only z's and V of x star. So. Anyone? Is this a positive definite matrix?
No.
Yeah, and why is it not?
You can check the first leading principal minor and it's 0.
Exactly. So if you just look at the principal minor 0, this is 0, and so this is not positive definite. It's not even positive semi-definite actually, because if you look at the second leading principal minor, this is -1. So it's not PD and not PST even. Okay. All right. So then we really have to rely on that V of x star condition. So we need to actually do a little more work to see if this is a local minimum or not. And this x star is a local minimum or not. So we basically need to check. Maybe I'll call it a different variable y, just for fun. L of x star lambda y needs to be bigger than 0 for all y not equal to 0, such that a gradient of hi I equal to 1, 2. Okay, so we need to check that. So let's check gradient of h1 x star transpose y. But that's the first row of that matrix A. So that's 1, 1, 0 times y, which is y1 plus y2. And we need to set this equal to 0. This implies that y1 is equal to minus y2. And then we also need to satisfy the condition with 0, 1, 1 here. So this says that y2 plus y3 is equal to 0, which means that y2 is minus y3, or y3 is also minus y2. That's a better way to write it, I guess. So y3 is the same as y1, and they both equal minus y2. Okay, so you're not really checking this positive condition for all y, but only y that have these constraints on them. So let's actually check it for those y's. What happens to this product? So look at this product, which is this vector times this times this. So you multiply that out, you get times the vector minus y2 minus y3 minus y1 minus y3 minus y1 minus y2. Okay, you multiply all that out and you get, it's easy to see that this is minus 2 times okay. But then let's now impose our, we need to show that this is positive. But we know that y1 is minus y2. So this is minus y2 squared. And then I have y1 equal to y3, which are both equal to minus y2. So I get plus y2 squared. And then last term is again minus y2 squared because y3 is minus y2. So this cancel and you get plus 2y2 squared, which is positive if y is not equal to 0. So we have verified the second order sufficiency condition. Okay. So this is actually a very interesting example because it's an example for which the Hessian is not positive definite, but if we restrict our y's to belong to V of x star, you get something that's positive. All right, that means that our x star 201 transpose is a strict local minimum. For the optimization problem of f such that hi x equal to 0. And now, okay, we'll ask the question, just like you did in a couple of homework problems that you did in homework 3, in the last 2 homework problems, is this x star a global minimum as well? But for that, we actually need to even ask, does f have a global minimum at all? Okay. So let's look at the constraint set. The constraint set hx equal to 0 says that x1 is equal to 2 minus x2 and x3 is 1 minus x2. So that's what the two constraints tell us. So if we take x2 to minus infinity, we can take x2 to minus infinity and satisfy the constraint. Right? Because we can take x2 to minus infinity and then x1 is going, is going off to plus infinity, x3 is going off to plus infinity, but they all remain in the set, the constraint set hx equal to 0. Okay, so now I have a situation where I have a constraint set which is really not bounded because I can make the norm of x go to infinity on this set. So the set is not bounded. It's closed, but it's not bounded. Right? I mean, we already knew that because this is a hyperplane, right? That just defines a hyperplane. These constraints are hyperplanes. So what happens as now as x2 goes to minus infinity? What happens to the function f? So if you look at minus x1, x2 plus x2, x3 plus x1, x3, well, x1 is going to plus infinity, x3 is going to plus infinity, and x2 is going to minus infinity. Okay, so this whole thing is going to minus infinity. All the terms inside the bracket, inside the parentheses, they're all going to plus infinity, and there's a minus sign outside. So this is going to minus infinity. So the function is actually, so is the function coercive?
Oh, it's
What
going
is
to minus infinity.
Yeah. Repeat.
No.
What's actually coercive in this case? It's a negative of the function that's coercive. Okay. So if the negative of a function is coercive, then actually the function achieves its maximum, but it doesn't achieve its minimum, right? So basically this function is not going to achieve its its global minimum in this case, because it's basically, well, it's another way to look at it. There is no global minimum because the function can be made to go to minus infinity. Okay? So there's no global minimum on this set. So this x star has to only just be a local minimum. Okay. Remember, we saw a picture of something like this before, a function that looked like this, that was like that, right? Going like a mountain or something. So this, it goes off to minus infinity there. This is a local minimum, but it's not a global minimum. Okay. So that's the kind of stuff that's happening here. Any questions? It's a little harder to draw because this would be in 3 dimensions, but we saw a 1-dimensional example of a function that has a local minimum, but it's not a global minimum.
I have a question. So, in case that x2 go to infinity, but if x1 and x3, one of them go to plus infinity. So I don't know what happened in that case.
Oh, it doesn't matter.
Any conclusion?
It doesn't matter as long as I could show that there is some, there's some way to keep x in the constraint set and make the function go to minus infinity. Then it cannot have a global minimum. As long as you find one way in which to make the function go to minus infinity and still remain in the constraint set, then they cannot have a minimum because it can be made as, the function can be made as small as you want, so there is no minimum. Okay. So you don't have to look. You just need to show one example of a sequence of vectors that sits in the constraint set for which the function is going off to minus infinity. Then there's no global minimum. Okay. All right. Actually, it's a good time to take a break. Actually, it's 11:43. So let's reconvene at 11:45. Any other quick questions about this? Or you can think about it some more, and then after the break, you can ask a question. Okay, so 2 minutes, back 11:45. So actually, and you guys might want to also think about whether this has a global max. So maybe think about whether you can construct a sequence of vectors x whose magnitude goes to infinity, and then if you can make the function also go to infinity, then it won't even have a global max. Actually, this function has neither. Okay, neither a global max nor a global min. Okay.
I have a question. So, could you repeat why fx goes to negative infinity? Because if I plug in hx equal to 0, basically x1 equal to 2 minus x2, x3 equal to 1 minus x2 into the fx, then
So that's what I'm doing here. If I take x2 to minus infinity, x1 is going to plus infinity, x3 is going to plus infinity, x1 times x3 is going to plus infinity, x2
yeah,
times,
but if I plug them in, there's some element canceled out, and then inside the parentheses it gives me minus x2 squared plus 2.
yeah, but there's a minus. There's these are just linear functions, right?
Yeah. So, but inside the parentheses, so there is a minus x2 squared plus 2. So inside the parentheses, it will go to negative infinity, but with a minus sign outside, then it will go to positive infinity.
No, it's the other way around.
Because I find there's some term canceled out in the if you plug them in.
Okay. Let's see. x2 is going to x3 is going to plus infinity. This is minus. Oh, I see. Okay, so the examples should have been the other way around. So sorry, take x2 to plus infinity in this case.
Oh, I see.
Then it'll work, right?
But yeah. Even if it's to plus infinity, because maybe we could try just because I get the final fx equal to x2 squares.
So x2, if x goes plus infinity, then this is going to go to plus infinity. 2 minus minus. I thought this example didn't have a global min. There's a way to do this.
So this is the final result I got for fx if we use x2 to represent.
Yeah. So you can take any variable, I guess, to plus infinity. Wait a minute. See. Of course. So that doesn't make sense. This is a product of these things. There must be a way to do this. I thought it was neither global min nor global max. Let's see. I'm going to, okay, so this is minus. Okay. Let's just write down what this is. Okay, so x1 is okay, 2 minus x2 times x2, then x2, x3. So I'll write that as 1 minus x2, x2 plus everything written in terms of x2. Right? I can do this with any variable, but maybe just that 2, 1 minus x2, and then when you simplify this, what do you get?
I get. I put in the chat box basically x2 squared is minus 2 at the end.
So minus 2
Oh.
minus x2 squared.
Yes.
Okay. Very good. So that's good. So this is actually it is a coercive function. I thought this was an example of which didn't have either. Okay, I stand corrected. I didn't think this through. Yeah, it is coercive because this can be done with any x, any vector x, and so this whole thing is just okay. I somehow thought that this product was inside was positive. Very good. All right. So Jason is correct. So this actually will go to infinity whenever the norm of x goes to infinity, plus infinity. Whenever the norm of x goes to plus infinity, because basically x, it's just the square of x2, and x1 is written in terms of x2. So any vector x for which the norm goes to infinity, this is going to plus infinity. So take that back. Global min exists. Implies this is x star is actually a global min, because we know it's a local min, and we have a coercive function on the set, on a closed set. Okay. All right. Actually, this is okay. Good. So, in fact, it illustrates the use of this result, the result that we went through the trouble of proving last time, right? So if we have a continuous function on a closed set S, which we have a closed set X, S, which is not compact, right? Because we can make X go to infinity, and we should just show that F is coercive in S, and it achieves its minimum. And so if we find a local minimum, it has to be the global minimum. Okay? All right. Good. I thought this was an example where neither one exists. Maybe there's another example we can create. Maybe we will talk about it on Thursday. I'll find an example where neither exists. All right. Any other questions? Let's do another case. Let's consider the case where we have linear constraints, but there is no regular x. Okay. So this is the case where the A1 through AM, the rows of this matrix, are not linearly independent. They're linearly dependent, basically. Okay. So if they're not linearly independent, then we know that the gradients of h at x, for any x that you could possibly consider, they're not Li. So there's no regular x. Okay. So since there's no regular x, we can't apply the Lagrange multiplier theorem. Okay. But it turns out that even though we can't apply the Lagrange multiplier theorem, there are Lagrange multipliers for this example. even when the A's are linearly dependent. And we'll see why. So let's say the A's are not linearly independent, and the rank of A is equal to K, which is less than M. Okay. So now let's reorder the AIs so that, so what I'm saying is that if they're not linearly independent, then I can only find, I can't, you know, I can only find K of these rows that are linearly independent, then the other guys have to depend on them. Okay, so the rank of A is strictly less than M. Okay, so now we reorder the AIs so that the top K of them are linearly independent. Okay, so then AI is the summation J equal to 1 to K alpha Ji times Aj for some alpha, some coefficients alpha, for I equal to K plus 1 through M. So if I look at the remaining AIs from K plus 1 through M, I can write them as linear combinations of the first K AIs. Okay. And the coefficients are some alpha Jis. Okay. Now, when we write constraints like this, so we have these constraints, you know, A1x equal to B1 up to AMX equal to BM. So if these constraints are not consistent with each other, that means there is no X that satisfies these things. Right? That can happen. Of course, we're going to rule out such possibilities. Okay, if these constraints are not going to be consistent, so basically, when I say that the first K of these guys are linearly independent, and the other guys are linear combinations of them, so then the B's have to be the corresponding linear combinations of the B's from the first K. Otherwise, these equations are not going to be consistent. Okay, so for them to be consistent and for AX equal to B to have at least one solution, we must have that the BI's must also be the same linear combinations of the B's. Everyone see that? For I equal to K plus 1 through M. So in this case, basically what this is saying is that these remaining constraints are, so if I go up to BK here, dot AKX equal to BK, then these are all that I need, because the remaining ones are going to be just derived from the first K constraints. So the last M minus K constraints are going to be redundant, because the same information is contained in the first K constraints. Are redundant. And you can discard them. So if that's the case, I can write my constraint optimization problem of minimizing fx over ax equal to b as equivalent to minimizing fx over this new constraint so new set of constraint equations that only contain k constraints now. And the A tilde matrix is just the first k rows of the A matrix, and the B tilde is the first k elements of the B vector. So now we have a situation where A tilde is full rank, with rank k constraints, they are linearly independent. And so there's a solution. So Lagrange multipliers exist for this problem, which is equivalent to this problem. So we'll instead solve this problem, for which we know Lagrange multipliers exist. So we can apply the same methodologies we just discussed for the previous example in this case. So this is a special case where even though in the original problem we don't have regular x, we can convert it to a problem for which we have regular x and for which Lagrange multipliers exist. Okay. Another way to think now, of course, the size of the Lagrange multiplier vector is no longer m, it's actually k, which is smaller than m. But you can think of if you want to think of it as a m-dimensional Lagrange multiplier, you can set the remaining coefficients to 0 without loss of generality. So there will only have to be k non-zero Lagrange multipliers. But there's another interesting fact here, is that you don't have uniqueness anymore. And the reason why you don't have uniqueness is because the A tilde, B tilde may not be unique. Because I could have chosen some other set of k linearly independent vectors to construct my A tilde. Okay. So this means that lambda may not be unique. And we'll see that in an example. Okay. The x star, for a given x star, the lambda may not be unique, depending on how you construct your A tilde matrix. Let's do an example. All right, so you have this convex function with these linear constraints. Actually, convex function with convex constraints. So you know that there's, every local minimum has a global minimum for this function already beforehand. But what we care about now is that these constraints are actually redundant. Okay, they're going to be, if I look at the A matrix, I'm going to have stuff that's linearly dependent. And then what we're going to focus on is to show that the Lagrange multipliers may not be unique in this case. So let's see what we do in this case. So we know that this A matrix is 1, 1, 0 from the first equation, 0, minus 1, 1 from the second equation, and 1, 0, 1 from the third equation. And the rows are obviously linearly dependent, because if I add the first two rows, I get the last row. If you look at the gradient of the function, you get 2x1, 2x2, and then 4x3 as the components. Okay, so let's take our first choice to be the first two rows, which are linearly independent, right, of this matrix. But I have other choices, right? I could choose the second and third row, for example, or the first and third row. They're also linearly independent, but I'll choose the first two in this case. And so let's say I get 1, 1, 0, 0, minus 1, 1, and the B tilde will be 2 and 1. Okay? And let's solve. so we know now that we can solve for x star and lambda, because we know now we have a problem for which x is regular, all x's are regular actually, and so we can apply the Lagrange multiplier theorem. So let's write down the Lagrange multiplier things first. So lambda 1 equals minus 2x1 star x1 star from the first from basically this one, and then this will be lambda 1 minus lambda 2 equals 2x2 star. Minus 2, so sorry. And then the last equation will be lambda 2 equals minus 4x3 star. Okay, and then we addition to that, we have the constraint equations x1 star plus x2 star equals 2, and x3 star minus x2 star equal 1. Okay, and putting it all together, if you just subtract from these two equations, from these three equations actually, you conclude that minus 2x2 star is minus 2x2 star is 4x3 star minus 2x1 star. Okay. Lambda 1 minus lambda 2. So this says that x2 star is x1 star minus 2x3 star. Okay. And then we can plug that in here. So this equation is this, then we have x1 star plus x2 star equal to 2. That's from this equation. Combine them, and you conclude that 2x2 star plus 2x3 star equal to 2. We're adding these two. And that implies that x2 star is 1 minus x3 star. If you plug that in to the other equation, into this equation, you get that, you get, if you solve for x3 star. So this implies that x3 star is equal to 1. And that implies that x2 star equal to 0 from up here. And then finally, this implies that x1 star is equal to 2. Okay, and then lambda 1 equals minus 4 from that first equation up there, and lambda 2 is also minus 4. X1 star is, x3 star is 1, so minus 4 x3 star. Okay. Okay, I'm not going to go over the rest. You could actually show that this is the global minimum of this problem, but you can go ahead and show that at home. What I want to illustrate, and I have a few minutes to do that, is what happens if I change my A tilde matrix. So you can think of this as a situation where lambda 1 is minus 4, lambda 2 is minus 4, and lambda 3, the third one, is actually 0, if you want to think of it that way. So now let's see what happens if I take this and this as my A tilde, the first and third rows. Okay, and you can try out other things at home, the other two, other combination at home. The remaining one. Okay, so this is my A tilde, and B tilde is 2, 3. Okay. So now you get that just plugging in. Now lambda 1 plus lambda 2 will be the first component of the negative of the gradient of f, which is minus 2. if you remember this, 2x1 star. And then the second one will give me lambda 1 equals minus 2x2 star. And the third one says that lambda 2 is minus 4x3 star. And if you by adding the second and third equations and making that equal to the first one, you get x1 star should be x2 star plus 2x3 star. And then you also have the constraints that x1 star plus x2 star equals 2, x1 plus x3 equals 3. Okay. And so again, solving, this is straightforward solving. From this equation up here, apply that in here, x1, x2 star minus 2x3 star equals 0. And this implies that adding these two, you get 2x1 star minus 2x3 star equal 2. So x1 star minus x3 star equals 1. Okay. And then we have x1 star plus x3 star is 3 up there. So we can solve for this. This implies that x1 star equals 2 and x3 star equals 1. Okay. And then x2 star we can get from one of those other equations. So it's x1 star is 2, so x2 star is 0. So let's go back to the previous page. Then the solution was x3 star is 1, x2 star is 0, x1 star is 2. So it's basically x is 2, 0, 1 transpose, and we get the same thing here. X, so maybe I should say x star. Yeah. So it's the same as in choice 1. But let's look at the lambdas now. So lambda 1 is minus 2x2 star in this case, which is 0. And lambda 2 is minus 4x3 star, which is still minus 4. Okay, so that's different from the lambdas we saw here, which minus 4 and minus 4. Okay, so the Lagrange multipliers are not unique for the given x star. So actually there's only one x star in this case. And so you just check for that x star whether the Lagrange multipliers are unique, and they're not unique in this case. So even if you want to think of the Lagrange multiplier corresponding to the row that we took off as 0, what you'll get then is, in this case you had minus 4, 0, and in this case you're going to get 0, 0, minus 4. So the Lagrange multipliers are quite different for the two choices of 8 tilde. Okay. Any questions? Pretty clear?
Clear.
Okay. All right. So yeah. So we need, by the way, a quick example of a function that's, that's for which there's neither a minimum nor a maximum. Maybe that allow us to construct an example, which I was hoping I would to do for this, here. So yeah, so for this case. Just a one-dimensional example for which there's no minimum or maximum.
X cubed.
Yeah, what did you say?
X cubed.
X cubed, yeah, X cubed is good. Just linear also, right? Just X. There's no minimum or maximum for that function. And so I think, yeah, so this function has a global minimum. Okay, that's interesting. Yeah, because of this, there's these products, I guess. If I remove one of the products, I could make this function not have a minimum or a maximum, one of the two, or neither. What could I do to this function to make that happen? But then I'll have to, change. Let me work something out, and maybe on Thursday we can talk about an example like that. Okay, for which we'll have a. We did look at a one-dimensional example before, right, in the previous lecture, which had a property like that. But yeah, we want to look at it with constraints. So. Yeah. So if you make one of these guys linear, probably you'll end up with something like that. But we have to still wonder whether there's a local minimum in that case or not. Yeah. So for example, if you took this one of these guys, just made the second term just x2, we'll probably be able to create an interesting case. All right. Okay. I think we're almost out of time, so we'll talk more about other interesting examples on Thursday. Okay. See you guys then.